Today, I want to take you on a journey into one of the greatest mysteries of the cosmos, a tale that challenges our understanding of the universe itself. Have you ever wondered what makes up most of the universe, yet remains invisible, elusive, and enigmatic? Today, we explore the fascinating realms of dark matter and dark energy. If you find this journey intriguing, please like and share to spread the wonder of cosmic discovery. The universe as we see it, the shining stars, swirling galaxies and radiant nebulae, forms only a small fraction of everything that exists. Beyond the visible, hidden from our sight and beyond the reach of ordinary instruments, lies a vast ocean of unseen entities shaping the cosmos. The evidence for these mysterious components first emerged from careful observations of how galaxies move and how the universe expands. Scientists noticed that the gravitational pull from visible matter, the stars, gas, and dust, was not enough to hold galaxies together or explain the speed of their rotation. Something invisible must be present, exerting gravitational force without, emitting light or radiation. This unseen mass was named dark matter, a placeholder for an unknown substance that dominates the mass of the universe. Dark matter does not shine, absorb, or reflect light, making it completely invisible to our telescopes. Yet its gravitational fingerprint is everywhere, sculpting the large-scale structure of the cosmos, guiding the formation of galaxies, and influencing the cosmic web connecting clusters of galaxies across immense distances. Parallel to this enigma is another profound mystery, dark energy. Discovered later through the study of distant supernovae, dark energy appears to be a force driving the accelerated expansion of the universe. Unlike gravity, which pulls matter together, dark energy pushes space apart, causing galaxies to drift away from each other faster and faster. Together, dark matter and dark energy make up about 95% of the universe's total content, leaving the ordinary matter, the atoms composing stars, planets, and ourselves, as just a tiny fraction. These discoveries have revolutionized cosmology, demanding new physics beyond the familiar laws and particles. What exactly are dark matter and dark energy? How do we detect what cannot be seen? What implications do they hold for the fate of the universe? Our story begins with the pioneering observations that first hinted at their existence. In the 1930s, astronomer Fritz Zwicky studied the Coma cluster of galaxies. By measuring how fast galaxies moved within the cluster, he calculated that there must be far more mass than what was visible. Without this extra mass, the cluster would fly apart. This invisible mass was what he called dunkle Materie, or dark matter. Over decades, further observations strengthened this idea. Vera Rubin's work on galaxy rotation curves in the 1970s revealed that stars at the edges of galaxies orbit just as quickly as those near the center, contradicting expectations from visible matter alone. The flat rotation curves indicated that galaxies are embedded in vast halos of dark matter, extending far beyond the luminous stars. Parallel to the quest for dark matter, scientists began examining the large-scale structure of the universe and its expansion. The Big Bang theory predicted a slowing expansion due to gravity. Yet, in the late 1990s, observations of distant type Ia supernovae revealed that the expansion is accelerating. This unexpected acceleration could only be explained by a mysterious repulsive energy permeating space, dubbed dark energy. While dark matter clusters and pulls galaxies together, dark energy pushes the universe apart, working on scales far larger than galaxies. The interplay between these invisible forces governs the cosmos' past, present, and future evolution. Current models estimate that dark matter constitutes roughly 27% of the universe, while dark energy makes up about 68%. Together, they dominate cosmic dynamics and structure formation. Ordinary matter, including everything we know and see, accounts for a mere 5%. This profound imbalance challenges our understanding of nature and compels physicists to search for new particles, new forces, and new theories. Numerous experiments worldwide aim to detect dark matter particles directly or indirectly. Underground, detectors shielded from cosmic rays seek rare collisions between dark matter particles and atomic nuclei. Particle colliders try to produce dark matter in high-energy collisions, while astrophysical surveys map the universe's structure to glean clues about dark matter's behavior. The quest to understand dark energy is equally ambitious, involving precise measurements of the universe's expansion history and the growth of cosmic structures. Space missions and ground observatories use supernovae, galaxy clustering, and cosmic microwave background radiation to constrain dark energy's properties. Despite the wealth of data, the true nature of dark matter and dark energy remains elusive. Are they new particles, unknown fields, or manifestations of deeper physical principles yet to be discovered? Our story continues as scientists probe these mysteries, pushing the boundaries of knowledge. The invisible scaffolding of dark matter and the mysterious force of dark energy together form the vast unseen majority of our universe, shaping everything from the tiniest particles to the largest cosmic structures. Understanding these components holds the key to comprehending the universe's origin, evolution, and ultimate destiny. This journey of discovery invites us to look beyond the familiar, to embrace the unknown, and to marvel at the cosmic tapestry woven by forces beyond sight. The vastness of the universe is punctuated not only by the light of countless stars, but also by the silent presence of forces and substances we cannot see. Dark matter, though invisible, leaves unmistakable traces through its gravitational influence on visible objects. Its existence is one of the most compelling enigmas in modern astrophysics. The search to understand dark matter invites us to explore realms far beyond ordinary matter, venturing into the frontiers of particle physics, cosmology, and astronomy. Our journey deepens as we consider the different candidates proposed for what dark matter might be. For decades, scientists have hypothesized that dark matter could consist of yet undiscovered particles, often called WIMPs, weakly interacting. Massive particles. These particles would interact with normal matter only through gravity and perhaps the weak nuclear force, making them extraordinarily difficult to detect. They would have mass and exert gravitational pull, yet remain imperceptible to light and electromagnetic radiation. Experiments such as those conducted deep underground in highly shielded environments attempt to catch the rare interaction of a WIMP with atomic nuclei. Although no definitive detections have been made yet, the search continues with ever-increasing sensitivity. Another compelling candidate for dark matter is axions, hypothetical ultra-light particles that could have been produced in the early universe. Axions would behave differently from WIMPs, and might reveal themselves through subtle effects on electromagnetic fields or in specially designed experiments involving strong magnetic fields and sensitive detectors. Some theories propose sterile neutrinos, a type of neutrino that does not interact through the weak force but only via gravity. These neutrinos could contribute to the dark matter budget, though their properties and existence remain speculative. Beyond particle candidates, alternative theories have emerged, attempting to explain dark matter without invoking new particles. Modified gravity theories, for example, suggest that the laws of gravity themselves may differ on cosmic scales, altering how matter behaves in ways that mimic dark matter's effects. While intriguing, these models face challenges when confronted with observations like the bullet cluster, a cosmic collision where the distribution of mass mapped by gravitational lensing clearly separates from visible matter, strongly supporting the existence of dark matter as a distinct entity. In addition to dark matter, dark energy presents a profound challenge to physics and cosmology. Its nature is even more mysterious, as it permeates all of space and drives the accelerated expansion of the universe. Dark energy could be a cosmological constant, a fixed energy density inherent to space itself, as originally proposed by Einstein. If so, it represents a fundamental property of the vacuum, an energy intrinsic to empty space that exerts a repulsive force. Alternatively, dark energy could be dynamic, evolving over time as a field called quintessence. Unlike a constant, this energy could vary in strength and influence, opening possibilities for a changing cosmic acceleration. Understanding dark energy requires probing the universe's expansion history with exquisite precision, mapping the brightness and redshift of distant supernovae, the clustering of galaxies, and the cosmic microwave background radiation left over from the Big Bang. Together, these observations weave a complex portrait of how the cosmos has grown and stretched over billions of years. The interplay between dark matter and dark energy shapes the cosmic web, the vast network of filaments, clusters, and voids that define the large-scale structure of the universe. Dark matter's gravity pulls matter into dense regions, forming galaxies and clusters, while dark energy pushes these structures apart, accelerating the universe's expansion. This delicate balance governs the destiny of all cosmic matter and energy. In our quest to understand these invisible components, new technologies and observational methods have been developed. Gravitational lensing, for instance, uses the bending of light by gravity to map the distribution of dark matter, revealing halos and filaments that are otherwise unseen. Cosmic microwave background measurements provide a snapshot of the early universe's conditions, encoding information about the amounts and properties of dark matter and dark energy. These observations have refined our models, constraining the possible characteristics of these mysterious components. Theoretical physicists strive to integrate dark matter and dark energy into a unified framework, exploring possibilities such as supersymmetry, extra dimensions, and modifications to fundamental forces. Such advances could revolutionize our understanding of the cosmos and the laws governing it. While the challenges are immense, the pursuit is a testament to human curiosity and ingenuity, pushing the boundaries of knowledge and technology. In the shadowy realm of dark matter and dark energy, each new discovery brings us closer to unraveling the cosmic mysteries that have fascinated humanity for centuries. This invisible majority holds the secrets to the universe's past and future, inviting us to imagine realities beyond our senses and to explore the profound depths of existence. The story of dark matter and dark energy unfolds across cosmic epochs, tracing a timeline from the earliest moments after the Big Bang to the vast expanse we observe today. Understanding their origins is essential to grasping their role in shaping the universe's past, present, and future. Shortly after the Big Bang, the universe was a hot, dense plasma of particles and radiation. In this primordial soup, matter and energy interacted in complex ways, giving rise to the seeds of cosmic structure. Dark matter, unlike ordinary matter, did not interact strongly with radiation, allowing it to begin clumping together under gravity earlier and more efficiently. These clumps served as the gravitational scaffolding upon which ordinary matter gathered to form the first stars and galaxies. Without dark matter, the universe's large-scale structure would look drastically different, and the process of galaxy formation would be slower and less efficient. Observations of the cosmic microwave background, CMB, the faint afterglow of the Big Bang, provide a snapshot of the universe approximately 380,000 years after its inception. The tiny fluctuations in temperature and density imprinted on the CMB encode vital information about the amounts and nature of dark matter and dark energy. Satellites such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck mission have mapped these fluctuations with unprecedented precision, allowing cosmologists to construct detailed models of the universe's composition and evolution. These models reveal that dark matter made up about 25% of the universe's total energy density at that time, while dark energy's influence was negligible in the early universe. Dark energy, as a mysterious force driving accelerated expansion, becomes dominant only in the relatively recent cosmic past, roughly 5 billion years ago. Before then, the universe's expansion was decelerating due to the gravitational pull of matter, both dark and ordinary. But as the universe expanded and matter became more diffuse, dark energy's repulsive effect took over, causing the expansion to speed up. This discovery, made by observing distant Type Ia supernovae, reshaped our understanding of the cosmos. The nature of dark energy remains one of the deepest questions in physics. Is it a true cosmological constant, fixed and unchanging? Or is it dynamic, perhaps evolving over time? If dark energy changes, it could have profound implications for the universe's fate. For example, a gradually increasing dark energy density could lead to a big rip, tearing apart galaxies, stars, and eventually atoms. Alternatively, if it fades, the expansion might slow or even reverse. Meanwhile, dark matter continues to play a vital role in structuring the cosmos. Its gravitational influence is visible not only in galaxies and clusters, but also in the vast filaments and voids that compose the cosmic web. This large-scale structure is like a spider's web spanning billions of light-years, with dark matter forming the framework upon which luminous matter hangs. Advanced simulations, such as the Millennium Simulation and Illustries, model the evolution of dark matter and galaxies over cosmic time. These virtual universes help scientists compare theoretical predictions with observations, refining our understanding of the nature of dark matter and the processes that shape cosmic structures. Yet, despite its gravitational dominance, dark matter remains elusive at the microscopic level. Unlike ordinary matter, it does not form atoms, molecules, or complex structures. It does not emit, absorb, or reflect light, making it invisible to telescopes. The leading hypothesis is that dark matter consists of particles yet unknown to science, interacting primarily through gravity and possibly the weak nuclear force. The search for these particles spans multiple approaches. Direct detection experiments aim to observe collisions between dark matter particles and nuclei in ultra-sensitive detectors buried deep underground. These experiments require shielding from cosmic rays and background radiation, as the expected interaction rate is extraordinarily low. Indirect detection searches look for signals produced when dark matter particles annihilate or decay, releasing gamma rays, neutrinos, or other particles. Observatories such as the Fermi Gamma Ray Space Telescope scan the cosmos for such signatures. Particle accelerators like the Large Hadron Collider attempt to produce dark matter particles in high-energy collisions, hoping to infer their presence from missing energy and momentum in the aftermath. Each method probes different aspects of dark matter's properties, complementing each other in the quest to unlock its nature. On the theoretical front, extensions to the standard model of particle physics propose new particles that could constitute dark matter. Supersymmetry, for instance, predicts partners for known particles, some of which are stable and could be WIMPs. Axions arise naturally in attempts to solve other physics puzzles and might also serve as dark matter candidates. The complexity and breadth of these efforts highlight the challenge and excitement of uncovering the nature of dark matter. Simultaneously, the nature of dark energy invites revolutionary ideas. Could it be related to the vacuum energy predicted by quantum field theory? If so, why is its measured value so small compared to theoretical expectations? A profound problem known as the cosmological constant problem. Or might dark energy arise from modifications of gravity at large scales, indicating new physics beyond Einstein's general relativity? Experiments and observations continue to seek clues. Large-scale surveys, such as the Dark Energy Survey and the upcoming Euclid mission, map the distribution of galaxies and cosmic structures, measuring the effects of dark energy on the universe's expansion and structure growth. By comparing these observations with theoretical models, scientists hope to constrain the properties of dark energy, perhaps uncovering its true nature. The entwined tales of dark matter and dark energy tell us that what we see, the stars, planets, and galaxies, is only the tip of the cosmic iceberg. The invisible majority shapes the destiny of everything, challenging our understanding and inviting us to explore deeper. The universe is a vast, mysterious place, and through these cosmic enigmas, we glimpse the profound beauty and complexity of the cosmos beyond the veil of light. To appreciate the profound impact of dark matter and dark energy, one must envision the universe not merely as a static collection of stars and galaxies, but as a dynamic, evolving tapestry woven by unseen forces. The intricate dance between these components orchestrates the cosmic symphony that governs the past, present, and future of everything that exists. Dark matter's gravitational pull acts like an invisible architect, sculpting the large-scale structure of the universe. It gathers into massive halos that envelop galaxies, providing the gravitational glue that holds stars, gas, and dust together. These halos also influence how galaxies merge and evolve, determining the formation of clusters and superclusters that stretch across hundreds of millions of light-years. Without dark matter, galaxies would lack the necessary mass to sustain their observed rotation speeds. Measurements of galaxy rotation curves reveal that stars in the outskirts orbit faster than expected if only visible matter were present. This discrepancy provides some of the earliest and strongest evidence for dark matter. Its gravitational presence alters the dynamics of galaxies, preventing them from flying apart despite their rapid rotation. In galaxy clusters, observations using gravitational lensing, the bending of light from distant objects by massive foreground structures, reveal mass distributions that cannot be accounted for by luminous matter alone. These measurements provide a three-dimensional map of dark matter's presence, showing vast regions rich in invisible mass. Meanwhile, the cosmic web emerges as a vast network of filaments composed largely of dark matter, connecting clusters and groups of galaxies. Within this web, ordinary matter flows along these filaments, fueling star formation and the growth of cosmic structures. The intricate patterns observed today originated from tiny quantum fluctuations in the early universe, amplified by gravity over billions of years. On a grander scale, dark energy exerts its influence by counteracting gravity's pull. The accelerated expansion of the universe discovered in the late 1990s suggests that a mysterious force pushes space apart. This expansion affects how structures form and evolve, determining the ultimate fate of the cosmos. If dark energy continues to dominate, galaxies will drift further apart, and star formation will gradually cease as gas supplies dwindle. The universe might enter a cold, desolate state, known as the heat death, where entropy reaches its maximum, and no useful energy remains to sustain processes. Alternatively, the nature of dark energy could alter this destiny, possibly reversing acceleration or causing catastrophic scenarios like the Big Rip. The balance between dark matter and dark energy is delicate and complex. Together, they form about 95% of the universe's total energy content, dwarfing ordinary matter, which makes up only around 5%. This realization has revolutionized cosmology, transforming our understanding from a universe dominated by visible matter to one governed primarily by unseen forces. Despite their invisibility, the effects of dark matter and dark energy ripple through every scale of the cosmos. From the smallest galaxies to the vast expanses of intergalactic space, these components define the shape, dynamics, and fate of the universe. The quest to understand them drives advances in both observation and theory. Cutting-edge telescopes and observatories, such as the James Webb Space Telescope, the Vera Rubin Observatory, and the Square Kilometre Array, are poised to deepen our understanding of cosmic structure and evolution. These instruments will map galaxies across cosmic time, reveal the distribution of dark matter with greater precision, and probe the effects of dark energy with unprecedented sensitivity. On the theoretical side, new frameworks in physics seek to unify dark matter and dark energy with the fundamental forces and particles known to science. Concepts like string theory, extra dimensions, and quantum gravity offer tantalizing possibilities, though much work remains to connect these ideas with observations. The pursuit of dark matter and dark energy also inspires profound philosophical reflections about the nature of reality. They challenge our perceptions of the cosmos, reminding us that what is visible constitutes only a small fraction of existence. The vast majority remains hidden, inviting curiosity, humility, and wonder. Humanity's quest to unveil these cosmic mysteries embodies the spirit of exploration that has driven scientific progress throughout history. From ancient stargazers to modern cosmologists, the search for understanding connects us across time and space. As technology advances and knowledge grows, we edge closer to revealing the true nature of dark matter and dark energy, unlocking secrets that will reshape our view of the universe and our place within it. In embracing the unknown, we affirm the power of human imagination and inquiry, illuminating the dark corners of the cosmos with the light of discovery. As we journey deeper into the cosmic mysteries of dark matter and dark energy, we find ourselves confronting the very limits of human knowledge in the frontiers of physics. The challenges in unraveling their secrets are immense, but so too is the potential for groundbreaking discoveries that could redefine our understanding of the universe. The experimental hunt for dark matter particles embodies one of the most ambitious endeavors in modern science. Because dark matter does not emit or interact with light, scientists rely on indirect clues and subtle interactions to detect it. Underground laboratories shielded from cosmic rays provide pristine environments for sensitive detectors designed to capture rare collisions between dark matter particles and atomic nuclei. These experiments employ a variety of technologies, including cryogenic crystals, liquid noble gases, and ultra-pure materials to reduce noise and background signals. Despite decades of effort, no conclusive detection has yet been made, but the search continues with increasing sensitivity. In parallel, astrophysical observations offer additional paths to probe dark matter. Gamma-ray telescopes monitor regions, such as the center of our galaxy, where dense concentrations of dark matter might produce annihilation signals. Neutrino detectors scan for telltale signs of dark matter interactions within celestial bodies like the Sun. Gravitational lensing studies map dark matter distributions across cosmic structures, refining models of its behavior and properties. These complementary approaches combine to constrain possible dark matter candidates and guide theoretical development. On the theoretical front, physicists explore a variety of dark matter models. Weakly interacting massive particles, WIMPs, have long been favored, motivated by extensions to the standard model of particle physics that predict stable, massive particles interacting via the weak nuclear force. Axions, another candidate, arise from efforts to solve problems in quantum chromodynamics and could form a cold, diffuse background of particles permeating space. More exotic proposals include sterile neutrinos, particles that interact only via gravity, and theories involving extra dimensions or hidden sectors. The diversity of models reflects both the complexity of the problem and the openness of scientific inquiry, where hypotheses evolve as new data emerges. Simultaneously, the quest to understand dark energy pushes the boundaries of cosmology and fundamental physics. If dark energy corresponds to Einstein's cosmological constant, it implies a fixed energy density inherent to the fabric of space-time. This interpretation faces the cosmological constant problem, where theoretical predictions of vacuum energy exceed observed values by an astonishing 120 orders of magnitude, a profound discrepancy challenging current physics. Alternative theories propose dynamic dark energy, embodied in fields such as quintessence, which evolve over time and space. Others suggest modifications to general relativity on cosmic scales, altering gravity's behavior to produce accelerated expansion without invoking an unknown energy component. Large-scale surveys mapping the distribution of galaxies and cosmic structures serve as crucial tests for these ideas. Measurements of baryon acoustic oscillations, the regular periodic fluctuations in matter density, imprinted by sound waves in the early universe, provide standard rulers for cosmic distances, helping constrain dark energy models. Likewise, observations of weak gravitational lensing, where the shapes of distant galaxies are subtly distorted by intervening mass, reveal how cosmic structures grow and evolve under the influence of gravity and dark energy. These data, combined with supernova observations and the cosmic microwave background, form a comprehensive picture that continues to sharpen our understanding. The interplay between theory and observation in the study of dark matter and dark Energy exemplifies the dynamic nature of scientific progress. Each discovery refines the questions we ask and the methods we employ, guiding the search forward. In this unfolding narrative, technological innovation plays a pivotal role, enabling measurements of unprecedented precision and scope. Instruments. Like the upcoming Vera Rubin Observatory will conduct wide-field surveys capturing billions of galaxies, mapping their distribution across space and time. The Euclid satellite will probe dark energy's effects on cosmic expansion and structure growth through high-precision imaging and spectroscopy. Meanwhile, next-generation underground detectors and accelerator experiments promise to extend the sensitivity of dark matter searches into uncharted territory. Together, these efforts paint a vision of a scientific revolution poised to transform cosmology and particle physics. Beyond the technical challenges, the mysteries of dark matter and dark energy invite reflection on the nature of reality itself. They remind us that much of the universe lies beyond direct perception, challenging the assumption that visible matter tells the whole story. The dark components shape the cosmic landscape, influence the formation of galaxies and stars, and determine the ultimate fate of the cosmos. They reveal a universe far richer and more enigmatic than previously imagined. Embracing these mysteries inspires humility and wonder. It highlights the limits of human understanding while igniting the spark of curiosity that drives exploration. As we delve into the unseen realms of dark matter and dark energy, we deepen our connection to the cosmos and expand the horizons of human knowledge. This journey continues, propelled by the relentless pursuit of discovery and the timeless desire to comprehend the universe we inhabit. The saga of dark matter and dark energy is a testament to humanity's relentless curiosity and ingenuity. Our story begins with the simple act of looking up at the night sky, observing stars and galaxies, and questioning the nature of the vast cosmos. Over centuries, these observations have evolved from mystical speculation to precise measurement, guided by the scientific method and powered by ever more sophisticated technology. The discovery of dark matter and dark energy stands as one of the greatest scientific revelations of our time, reshaping our understanding of the universe's composition, evolution, and destiny. One of the earliest clues to the existence of dark matter emerged from the study of galaxy rotation curves in the 1970s. Astronomer Vera Rubin's meticulous measurements showed that stars in the outer regions of galaxies orbited at speeds too high to be explained by visible matter alone. This anomaly suggested that a vast amount of unseen mass was influencing their motion, a hidden scaffolding upon which galaxies are built. This invisible mass was later termed dark matter. Beyond individual galaxies, clusters of galaxies provide additional evidence. The observed velocities of galaxies within clusters and the hot X-ray emitting gas confined by the cluster's gravity indicated far more mass than could be accounted for by luminous matter. Gravitational lensing studies further confirmed these findings, showing how massive clusters bend and distort light from background sources more than expected. Together, these observations established dark matter as a fundamental component of cosmic structure. The cosmic microwave background, CMB, the afterglow of the Big Bang, provides a snapshot of the early universe and another pillar of evidence. Precise measurements of the CMB's temperature fluctuations by missions such as COBE, WMAP, and Planck reveal the distribution of matter and energy fractions in the young cosmos. These data show that ordinary matter comprises only about 5% of the total mass energy, with dark matter making up roughly 27%, and dark energy about 68%. This detailed cosmological inventory has become a cornerstone of the standard model of cosmology, known as lambda cold dark matter, LCDM. Dark energy's discovery in the late 1990s added a new, surprising chapter. Observations of distant type Ia supernovae, exploding stars serving as cosmic distance markers, revealed that the expansion of the universe is accelerating, not slowing as once expected. This acceleration implied the presence of a mysterious, repulsive force permeating space, dark energy. The simplest interpretation is Einstein's cosmological constant, representing a constant vacuum energy density. Yet this raises profound theoretical challenges, such as explaining why its value is so small, but non-zero. The puzzle of dark energy remains one of the deepest in fundamental physics. Modern cosmology uses a variety of tools to study dark energy's properties. Large galaxy surveys map the three-dimensional distribution of matter, revealing how cosmic structures grow under the competing effects of gravity and accelerated expansion. Measurements of baryon acoustic oscillations serve as cosmic yardsticks, anchoring the distance scale across epochs. Weak gravitational lensing measures distortions in the shapes of distant galaxies, offering insights into the distribution of matter and the strength of gravity on large scales. These observational programs work together to constrain dark energy's equation of state, its relationship between pressure and density, and to test alternative gravity theories. Meanwhile, the search for the particle nature of dark matter intensifies. Experiments such as the Large Underground Xenon LWEX detector, Xenon-T, and PANDAX utilize ultra-pure liquid xenon targets deep underground to shield from cosmic rays. These detectors aim to catch the faint interactions between dark matter particles and atomic nuclei. Similarly, the Large Hadron Collider, LHC, explores possible production of dark matter candidates through high-energy particle collisions. Although no definitive signals have emerged, these experiments refine the landscape of viable models and guide future searches. Theoretical physicists explore beyond the standard model frameworks to account for dark matter and dark energy. Supersymmetry, a proposed symmetry relating particles of different spins, predicts stable dark matter candidates such as neutralinos. String theory, aiming to unify all fundamental forces, introduces extra dimensions and hidden sectors potentially linked to dark components. Some models propose that dark matter consists of primordial black holes or other exotic compact objects. Dark energy may stem from new scalar fields or modifications to gravity. Each approach brings unique insights and challenges, underscoring the complexity of these cosmic enigmas. The implications of understanding dark matter and dark energy extend beyond science. They touch upon philosophical questions about the nature of existence and our place in the universe. The realization that most of the cosmos is invisible and mysterious challenges our senses and intuitions. It invites us to embrace uncertainty and marvel at the vastness beyond immediate perception. Our cosmic journey is both a scientific and a human adventure, blending empirical rigor with awe and wonder. As we continue to probe the darkness that shapes our universe, we carry forward the legacy of discovery, curiosity, and imagination that defines humanity. The influence of dark matter and dark energy is not limited to abstract scientific concepts. It profoundly shapes the universe's architecture and the destiny of everything within it. Galaxies, stars, planets, and ultimately life itself owe their existence and evolution to these invisible components. Dark matter, by providing the gravitational framework, orchestrates the formation of cosmic structures, while dark energy dictates the grand expansion, stretching space itself. This interplay determines the cosmic timeline and the conditions for complexity to emerge. To comprehend the role of dark matter, imagine the universe as a vast cosmic web. This web consists of filaments and nodes of matter, predominantly dark matter, forming a skeleton around which visible matter gathers. Galaxies reside at the intersections of these filaments, where dark matter's gravity pulls in gas and dust to fuel star formation. Without this invisible scaffolding, the delicate processes leading to galaxy formation and evolution would be impossible. Observations reveal that dark matter halos envelop galaxies, extending far beyond their visible edges. These halos influence galaxy rotation curves, keeping stars bound within despite rapid orbital speeds. They also affect interactions and mergers between galaxies, triggering bursts of star formation, or the creation of elliptical galaxies through violent collisions. On larger scales, Clusters and superclusters of galaxies emerge as dense concentrations of dark matter. Within these structures, dark matter governs dynamics, binding galaxies together and preventing their dispersal. These massive halos also contain vast amounts of hot gas detectable in X-rays, contributing to the total gravitational mass. Studying these regions reveals insights into the nature and distribution of dark matter. Conversely, dark energy operates on the largest cosmic scales, acting as a mysterious repulsive force. It accelerates the expansion of space, causing galaxies and clusters to recede from one another at increasing speeds. This expansion shapes the universe's ultimate fate. If dark energy's influence grows stronger, it could lead to a scenario where galaxies become isolated, their light stretched beyond detection, and cosmic horizons shrink. Stars will exhaust their fuel, and the universe will enter a quiet, cold phase, devoid of new formation. Understanding the properties of dark energy is thus crucial to predicting the long-term evolution of the cosmos. The discovery of dark energy revolutionized cosmology. Before its revelation, scientists expected that the gravitational pull of matter would slow expansion. Instead, the observation of distant supernovae revealed acceleration, prompting a paradigm shift. This discovery earned the 2011 Nobel Prize in Physics and inspired numerous observational campaigns to probe the nature of this enigmatic energy. Measurements of the cosmic microwave background provide snapshots of the early universe, revealing the primordial fluctuations that seeded structure formation. These measurements, combined with galaxy surveys and supernova data, confirm the composition of roughly 68% dark energy, 27% dark matter, and 5% ordinary matter. This composition forms the basis of the current standard cosmological model. Yet, many questions remain. What exactly is dark energy? Is it a constant vacuum energy as Einstein's cosmological constant suggests, or does it vary over time and space? Could it arise from unknown fields or modifications to gravity? The answers to these questions are central to understanding the universe's fate and the fundamental laws governing reality. In parallel, the quest to identify the particle nature of dark matter continues. The lack of electromagnetic interactions means it remains invisible to conventional telescopes, but its gravitational fingerprint is unmistakable. Laboratory experiments aim to detect rare collisions between dark matter particles and ordinary atoms, while astrophysical searches look for indirect signatures of annihilation or decay. Advanced detectors deep underground, shielded from cosmic radiation, push the limits of sensitivity to uncover elusive interactions. Theoretical models propose various candidates, from weakly interacting massive particles, WIMPs, to axions, sterile neutrinos, and beyond. Each candidate carries distinct implications for particle physics and cosmology, motivating diverse experimental approaches. Simultaneously, collider experiments search for new physics that might produce dark matter particles under controlled conditions. The pursuit of dark matter and dark energy transcends disciplines, merging astrophysics, particle physics, cosmology, and mathematics. It inspires the development of new technologies, from sensitive detectors to powerful telescopes, driving innovation with broad applications. Moreover, these mysteries challenge our philosophical understanding of the cosmos. The realization that most of the universe's content is invisible and unknown humbles us, expanding the frontier of human knowledge and imagination. It beckons us to explore further, pushing the boundaries of science and thought. As our understanding grows, so does our appreciation for the complexity and beauty of the cosmos. The interplay of dark matter and dark energy shapes a universe that is dynamic, mysterious, and deeply interconnected. A universe that continues to invite exploration, wonder, and discovery. The journey to understand dark matter and dark energy is also a journey through time, tracing the history of the universe from its earliest moments to its far future. The Big Bang, an event marking the origin of space, time, and energy, set the stage for all cosmic evolution. In its aftermath, the universe expanded rapidly, cooling and allowing particles to combine, forming the first atoms. Yet this nascent universe was dominated not by ordinary matter but by dark matter and radiation. Dark matter began to clump under gravity, forming the seeds for the large-scale structures we observe today. The subtle density variations imprinted in the cosmic microwave background reflect these primordial fluctuations. Over billions of years, dark matter's gravitational pull drew ordinary matter into dense regions, triggering the formation of stars, galaxies, and clusters. These cosmic edifices grew in complexity, merging and evolving under the influence of dark matter's invisible hand. Meanwhile, the universe's expansion continued, governed first by radiation and matter, and, later about 5 billion years ago, dark energy began to dominate. This transition marked a profound shift in cosmic dynamics, turning the expansion from deceleration into acceleration. The implications of this change ripple across cosmic history and future. Understanding this timeline requires an intricate synthesis of observations, simulations, and theoretical insights. Advanced telescopes map the distribution of galaxies across cosmic epochs, revealing how structure formation evolved. Computer simulations model the gravitational collapse of dark matter halos and the interplay of gas, stars, and feedback processes. Together, these tools allow scientists to reconstruct the universe's story with increasing fidelity. The evolution of the universe under dark energy's influence leads to profound questions about its ultimate fate. If dark energy remains constant, the cosmos will continue to expand exponentially, cooling and diluting matter. Galaxies beyond our local group will become unreachable, and star formation will cease, ushering in a dark, quiet era sometimes called the heat death. Alternative scenarios propose dynamic dark energy that changes over time, potentially leading to a big rip, where space-time itself is torn apart, or a future collapse reversing the expansion. Each scenario challenges our understanding of physics and cosmology. These cosmological mysteries intertwine with fundamental physics at the smallest scales. Efforts to unify gravity with quantum mechanics, the elusive theory of everything, might shed light on the nature of dark energy and dark matter. Concepts like extra dimensions, supersymmetry, and quantum vacuum fluctuations offer tantalizing possibilities but remain unconfirmed. Unraveling these threads requires experiments at the frontiers of high-energy physics and precise cosmological measurements. Meanwhile, the study of dark matter and dark energy drives technological innovation. Instruments like the James Webb Space Telescope and future missions aim to probe the early universe, cosmic structure, and dark energy's effects with unprecedented accuracy. Ground-based surveys, such as the Vera C. Rubin Observatory's Legacy Survey of Space and Time, will map billions of galaxies, tracing the cosmic web and revealing subtle signatures of dark components. These endeavors represent human curiosity and collaboration on a global scale. The quest to comprehend dark matter and dark energy also inspires philosophical reflection. It invites us to ponder the limits of knowledge, the nature of reality, and our place in an immense cosmos largely hidden from view. The fact that most of the universe is dark, elusive, and unknown challenges anthropocentric views and expands our sense of wonder and humility. It exemplifies the spirit of exploration, pushing beyond the visible to uncover the invisible forces shaping existence. This grand narrative of a universe shaped and driven by unseen matter and mysterious energy reminds us that reality is often stranger than fiction. It encourages us to keep asking questions, seeking answers, and embracing the unknown with curiosity and courage. In this cosmic odyssey, dark matter and dark energy stand as symbols of mystery and discovery, of the profound interplay between observation and theory, and of the endless human drive to illuminate the darkest corners of existence. Exploring the cosmic tapestry woven by dark matter and dark energy requires a deep dive into the methods astronomers and physicists employ to observe and analyze these elusive phenomena. While dark matter cannot be seen directly, its gravitational effects on visible matter provide vital clues. One such method is gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. When light from distant galaxies passes near massive objects like galaxy clusters, the gravity of these objects bends and magnifies the light, acting like a natural cosmic lens. By analyzing the distortions in the shapes and brightness of background galaxies, scientists can map the distribution of dark matter, revealing structures invisible to traditional telescopes. This method, known as weak gravitational lensing, has become a powerful tool for studying the large-scale structure of the universe and the role of dark matter within it. Beyond lensing, the motion of galaxies within clusters and the temperature of hot intra-cluster gas offer additional evidence for dark matter. The observed velocities and thermal energy levels often exceed what visible matter alone can explain. These observations point to the presence of a dominant, invisible mass that binds clusters together, preventing them from flying apart. Astronomers measure these parameters through X-ray observations, radio waves, and spectral analysis, combining data across the electromagnetic spectrum to build a comprehensive picture of the cluster's mass composition. Dark energy, though even more mysterious, is probed through the study of cosmic expansion and large-scale structure growth. Observations of distant type Ia supernovae serve as cosmic mile markers, enabling precise measurements of how the expansion rate changes over time. These measurements unveiled the accelerated expansion, pointing to the presence of dark energy. Large galaxy surveys complement this by mapping the clustering and distribution of galaxies across vast distances, revealing how the growth of structure is affected by dark energy's repulsive influence. Additionally, the cosmic microwave background provides a snapshot of the universe approximately 380,000 years after the Big Bang, capturing the primordial density fluctuations that evolved into today's galaxies and clusters. Precise measurements of the CMB's temperature, anisotropies, and polarization patterns have enabled scientists to constrain the total amount of matter and energy in the universe, including the fractions attributed to dark matter and dark energy. Instruments such as the Planck satellite have refined these measurements, contributing to the widely accepted lambda cold dark matter model. Laboratory experiments seek to directly detect dark matter particles through their rare interactions with ordinary matter. Detectors placed deep underground, shielded from cosmic rays, aim to identify tiny energy deposits caused by dark matter particles colliding with nuclei. Though no confirmed detection has occurred yet, these experiments have significantly narrowed the parameter space for possible dark matter properties, guiding theoretical models and future searches. Particle accelerators like the Large Hadron Collider probe high energies where dark matter particles might be produced or inferred through missing energy signatures. The combination of astrophysical observations and particle physics experiments forms a multi-pronged approach, increasing the chances of unlocking the nature of dark matter. In parallel, theoretical work continues to explore possible dark matter candidates, including weakly interacting massive particles, WIMPs, axions, sterile neutrinos, and more exotic possibilities. Each candidate suggests unique detection strategies and cosmological implications. Dark energy theories also explore beyond the cosmological constant, considering dynamic fields such as quintessence, modifications to general relativity, and extra-dimensional effects. These theories strive to explain dark energy's observed properties while remaining consistent with cosmological data. Despite immense progress, fundamental questions remain unanswered. Why does dark energy have the precise value it does? What is the particle nature of dark matter? Are these two phenomena connected in deeper ways? Addressing these questions demands new physics and creative ideas, continuing the tradition of scientific inquiry and discovery. The pursuit of understanding dark matter and dark energy embodies the spirit of modern science, combining observation, theory, technology, and collaboration to unravel the universe's deepest mysteries. It reminds us that the cosmos is far more complex and wondrous than our everyday experience suggests, inviting us to keep exploring with open minds and eager hearts. The quest to uncover the mysteries of dark matter and dark energy has spurred remarkable technological advances and international collaborations, transforming how humanity studies the cosmos. Cutting-edge observatories, both ground-based and spaceborne, are designed to probe deeper and more precisely than ever before. The Vera C. Rubin Observatory, with its expansive camera and wide field of view, is set to conduct the legacy survey of space and time, capturing billions of galaxies over a decade. This vast data set will enable astronomers to map the distribution and growth of cosmic structures with unprecedented detail, shedding light on dark matter's influence and dark energy's role in cosmic expansion. Similarly, the European Space Agency's Euclid mission aims to explore dark energy by surveying billions of galaxies across cosmic time, measuring their shapes, and clustering to trace how the universe's expansion rate changes. NASA's Nancy Grace Roman Space Telescope will complement these efforts with wide-field imaging and spectroscopy, targeting supernovae, galaxy clusters, and gravitational lensing signals. These observatories exemplify the power of international scientific cooperation, bringing together thousands of researchers worldwide. The data collected will challenge and refine cosmological models, providing stringent tests for theories of dark matter and dark energy. On the theoretical front, researchers develop sophisticated computer simulations that model cosmic evolution under different assumptions about dark matter and dark energy properties. These simulations recreate the formation of galaxies and large-scale structures, allowing scientists to compare theoretical predictions with observational data. They also explore the impacts of different dark matter candidates, such as cold, warm, or self-interacting dark matter, on structure formation and galaxy morphology. These insights help narrow down viable models and guide future observations. Beyond astrophysics, the investigation of dark matter and dark energy intersects with fundamental physics. Experiments in particle physics seek to produce or detect dark matter particles directly, while theorists explore frameworks beyond the standard model, such as supersymmetry, extra dimensions, and string theory. The hope is that these approaches will converge, revealing the true nature of the dark sector. Meanwhile, philosophers and historians of science reflect on the profound implications of discovering that most of the universe is made up of invisible, unknown substances and energies. This challenges human-centric perspectives and invites contemplation about the limits of perception and understanding. It also underscores the iterative nature of science, where each answer opens new questions and expands horizons. The journey to comprehend dark matter and dark energy is emblematic of humanity's enduring curiosity and capacity for wonder. It connects the tiniest particles to the vastest cosmic scales, linking the fabric of space-time to the emergence of galaxies and life. It reveals a universe far more intricate and mysterious than previously imagined, where the visible is but a fraction of the whole. As new discoveries unfold, they will inspire future generations to explore, imagine, and understand, continuing the timeless quest to unravel the cosmos. This pursuit not only enriches scientific knowledge, but also enriches our appreciation of existence itself, reminding us that even in the darkness, there is light, illumination born from curiosity, knowledge, and the shared human spirit. The invisible forces shaping our cosmos, dark matter and dark energy, fundamentally alter our understanding of space, time, and reality itself. Dark matter acts as the gravitational scaffolding upon which galaxies, stars, and planets assemble, its silent presence enabling the complex cosmic structures that define our universe. Yet despite decades of research, the exact nature of these particles remains one of the most profound enigmas in physics. Dark energy, by contrast, accelerates the expansion of space, pushing galaxies apart with a mysterious, repulsive force. It challenges the very fabric of physics and cosmology, suggesting that the universe is far more dynamic and strange than classical theories predicted. The interplay between these two dark components governs the universe's evolution on the grandest scales, from the formation of the first galaxies to the ultimate fate of all matter and energy. Understanding dark matter and dark energy demands not only advanced technology and intricate observations, but also bold theoretical leaps. Physicists ponder new particles, unknown forces, and extra dimensions that might reconcile the dark sector with the well-tested standard model of particle physics. Theories of quantum gravity and string theory offer tantalizing hints but remain unverified. At the same time, astronomical observations grow ever more precise, with surveys capturing billions of galaxies and mapping cosmic structures in exquisite detail. These data sets challenge existing models and hint at new physics yet to be discovered. The synergy of observational cosmology, particle physics, and theoretical frameworks forms a vibrant frontier where mysteries meet breakthroughs. On a philosophical level, the existence of vast dark components invisible to our senses invites reflection on the limits of human perception and knowledge. It reveals a cosmos where much lies beyond direct observation, accessible only through indirect evidence and inference. This perspective humbles us, inspiring awe and curiosity as we seek to unveil the hidden layers of reality. Our journey to decode dark matter and dark energy is a testament to human ingenuity and persistence. It transcends disciplines and borders, uniting scientists worldwide in a shared quest to illuminate the darkness. The answers we find will reshape our cosmic story and deepen our connection to the universe. In embracing the unknown, we celebrate the spirit of discovery that defines our species. The dark side of the universe is not merely a void or absence, but a realm rich with secrets that may transform our understanding of existence itself. Among the many hypotheses proposed to explain dark matter, one of the most compelling is the idea of weakly interacting massive particles, or WIMPs. These theoretical particles, predicted by extensions of the standard model of particle physics, would interact with ordinary matter through gravity and the weak nuclear force, but not electromagnetically, making them effectively invisible to light and other electromagnetic radiation. Their massiveness suggests they could clump together under gravity, forming the invisible halos surrounding galaxies and clusters observed through gravitational effects. Detecting WIMPs directly involves incredibly sensitive experiments designed to observe rare interactions between these particles and atomic nuclei. These detectors, often located deep underground to shield them from cosmic rays and background radiation, use materials such as xenon or germanium to sense minute energy transfers. Despite years of effort, no conclusive evidence has emerged, pushing scientists to refine their techniques and explore alternative candidates. Another intriguing possibility is the axion, a hypothetical ultralight particle originally proposed to solve a different puzzle in particle physics, the strong CP problem. Axions, if they exist, could form a pervasive cosmic field that behaves as cold, dark matter. Specialized experiments aim to detect axions by converting them into photons in strong magnetic fields, employing resonant cavities and sensitive radio receivers. The diversity of dark matter candidates reflects the richness of theoretical ideas and the challenges posed by the unknown. Beyond WIMPs and axions, models include sterile neutrinos, particles that do not interact via the weak force, but may influence cosmic structure formation, and primordial black holes, tiny black holes formed in the early universe that could constitute a fraction of dark matter. Each candidate has unique implications for cosmology, galaxy formation, and particle physics, making the search a multifaceted scientific adventure. Meanwhile, the nature of dark energy remains even more elusive. The simplest explanation is the cosmological constant, an intrinsic energy density of empty space proposed by Einstein, and consistent with a constant dark energy density over time. However, this solution raises profound questions about the vacuum energy predicted by quantum field theory, which exceeds observed values by many orders of magnitude, a discrepancy known as the cosmological constant problem. Alternative explanations posit that dark energy is dynamic, arising from a scalar field slowly evolving over cosmic time, akin to the inflaton field responsible for cosmic inflation. These quintessence models allow dark energy's strength to vary, potentially observable through detailed measurements of cosmic expansion history and structure growth. Other ideas explore modifications to gravity itself, proposing that general relativity may need adjustment on cosmological scales. These theories predict subtle deviations from standard predictions, testable with precise astrophysical observations. Despite the complexity and uncertainty, progress continues. Each new experiment, each improved measurement, each refined simulation brings us closer to understanding the universe's dark components. The interplay of theory and observation propels cosmology forward, revealing a cosmos both wondrous and mysterious, challenging our imagination and expanding our knowledge. The influence of dark matter extends far beyond merely shaping the large-scale structure of the universe. It profoundly impacts the formation and evolution of galaxies and stars. In the primordial universe, as matter began to clump under gravity, dark matter provided the gravitational wells into which ordinary matter, gas and dust, fell, eventually igniting the birth of stars and galaxies. These invisible halos acted as cosmic cradles, guiding the complex processes that led to the dazzling diversity of galactic forms we observe today. Without dark matter, the universe would be a vastly different place, less structured, less hospitable to life as we know it. Observations of galaxy rotation curves reveal the presence of dark matter halos extending far beyond the visible edges of galaxies. Unlike the motions predicted by Newtonian gravity based on luminous matter alone, stars orbit at unexpectedly high velocities in the outer regions, implying the existence of an unseen mass. This phenomenon provided some of the earliest strong evidence for dark matter and remains a cornerstone of modern cosmology. On smaller scales, dark matter influences star formation by affecting the density and distribution of gas clouds within galaxies. It shapes the gravitational potential wells where gas cools and condenses, enabling the collapse necessary to ignite nuclear fusion in stellar cores. Thus, the life cycle of stars, the chemical enrichment of the universe, and ultimately, the conditions for planets and life are intertwined with the presence of dark matter. Beyond galaxies, dark matter governs the clustering of galaxy groups and clusters. These vast assemblies of galaxies are held together by the gravitational pull of dark matter, which dominates their total mass budget. The hot gas permeating clusters emits X-rays, allowing astronomers to estimate the cluster's mass distribution, again confirming the dominance of dark matter. Additionally, the large-scale filamentary structure of the cosmos, the cosmic web, is shaped by the distribution of dark matter. Galaxies and clusters trace this vast network of filaments and voids, painting a picture of the universe's scaffolding. Simulations of cosmic evolution reveal how dark matter seeds this web, dictating the flow of matter and the environment for galaxy formation. While dark matter sculpts the universe's architecture, dark energy plays a contrasting but equally fundamental role by influencing the cosmic expansion rate. Since its discovery, dark energy's repulsive effect has accelerated the stretching of space itself, altering the timing and scale of structure formation. This acceleration impacts the fate of the universe, suggesting scenarios ranging from eternal expansion and gradual cooling to more exotic outcomes like the Big Rip, where space could ultimately tear apart. Understanding these cosmic influences requires integrating astrophysical observations across multiple wavelengths, sophisticated computer modeling, and the development of new theoretical frameworks. The synergy of data from telescopes, satellites, and particle experiments continues to refine our grasp of the universe's dark side. Through this grand endeavor, humanity inches closer to a unified picture of the cosmos, where dark matter and dark energy are no longer mysteries, but fundamental elements of reality. The vast, silent expanse of dark energy, driving the universe's accelerating expansion, invites profound questions about the ultimate destiny of all cosmic structures. As space stretches faster and faster, galaxies once gravitationally bound may drift beyond each other's observable horizons, leaving isolated islands of matter in a dark, ever-expanding sea. This inexorable acceleration suggests a future where the night sky dims and distant cosmic landmarks vanish from view forever, hidden beyond the limits of our observation. Such a fate challenges our notions of permanence and connection, reminding us of the dynamic and transient nature of the cosmos. Theories about dark energy's nature and behavior shape these projections. If dark energy remains constant, the universe will expand indefinitely, cooling and thinning over eons, a scenario known as the Big Freeze. Alternatively, if dark energy evolves or strengthens, more dramatic endings emerge. The Big Rip hypothesis envisions a future where dark energy's repulsive force grows so strong that it overcomes all gravitational, electromagnetic, and even nuclear forces, ultimately tearing galaxies, stars, planets, and atoms apart. These scenarios, while speculative, highlight the importance of understanding dark energy's properties. Observational efforts focus on measuring the equation of state parameter, which describes how dark energy density changes over time. By mapping distant supernovae, galaxy clusters, and cosmic microwave background fluctuations, astronomers seek subtle signatures revealing whether dark energy is static or dynamic. Simultaneously, theoretical physicists explore models beyond the cosmological constant, such as quintessence fields, phantom energy, or modifications to gravity, attempting to reconcile observations with fundamental laws. These endeavors have profound implications not only for cosmology, but for physics at large. Dark energy challenges Einstein's theory of general relativity and invites extensions that may unify gravity with quantum mechanics. Its discovery has revitalized the search for a deeper understanding of spacetime, vacuum energy, and the forces governing reality. The journey to comprehend dark energy exemplifies the interplay between observation, theory, and imagination in science. It expands our perspective beyond the visible universe, confronting mysteries that transcend daily experience and scale. Yet, within this vast unknown lies the potential for transformative insights, reshaping our understanding of existence. As we probe the dark energy accelerating the cosmos, we confront questions that resonate philosophically about impermanence, cosmic destiny, and humanity's place in the unfolding story of the universe. This pursuit inspires awe and humility, reaffirming the profound connection between scientific discovery and the human spirit. The cosmic microwave background radiation, a faint glow left over from the universe's infancy, provides one of the most crucial windows into understanding dark matter and dark energy. This relic radiation, permeating all of space, encodes the conditions of the early universe just 380,000 years after the Big Bang, when photons decoupled from matter and began traveling freely through space. By studying the minute temperature, fluctuations, and polarization patterns in this ancient light, scientists reconstruct the universe's composition, geometry, and evolution with remarkable precision. Observations by satellites such as the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck mission have revolutionized cosmology, revealing that ordinary matter constitutes only about 5% of the universe's total energy budget, with roughly 27% attributed to dark matter and 68% to dark energy. These findings underscore how dominant the dark components are in shaping cosmic history. The intricate patterns in the cosmic microwave background arise from the interplay of density fluctuations, acoustic waves, and gravitational effects in the early universe. Dark matter influenced these processes by deepening gravitational wells, enabling the growth of structure, while dark energy affected the universe's expansion rate, subtly modifying the imprint left on the radiation. Precise measurements of these patterns help refine cosmological parameters, testing different models of dark matter and dark energy. In addition to cosmic microwave background studies, large-scale galaxy surveys map the distribution of matter across billions of light-years. By examining the clustering and shapes of galaxies, astronomers trace the influence of dark matter halos and the expansion history dictated by dark energy. Techniques such as baryon acoustic oscillations provide standard rulers for measuring cosmic distances, enhancing our understanding of dark energy's effects. Gravitational lensing, the bending of light by massive objects, offers another powerful tool. Dark matter's gravitational fields distort the images of distant galaxies, allowing scientists to map its distribution even where no visible matter exists. Weak lensing surveys across vast regions of the sky reveal the cosmic web's structure and the growth of matter over time. These diverse observational approaches complement each other, creating a coherent picture of the dark universe. They constrain models, guide theoretical development, and inspire new experiments. The synergy between cosmic microwave background analysis, galaxy surveys, and gravitational lensing exemplifies the multi-messenger nature of modern cosmology. Together, these methods advance the quest to decode dark matter and dark energy, moving from mystery toward understanding. The pursuit of dark matter and dark energy has catalyzed a golden era of experimental ingenuity and technological advancement, ushering in a new generation of observatories and instruments designed to probe the universe's most enigmatic forces. From deep beneath the Earth's surface to the far reaches of space, scientists are deploying increasingly sensitive detectors, vast telescope arrays, and sophisticated satellites, all aimed at unraveling the invisible architecture of the cosmos. The Large Synoptic Survey Telescope, now named the Vera C. Rubin Observatory, represents one of the most ambitious ground-based efforts to chart the dynamic sky. By scanning the entire visible sky every few nights, it will create a time-lapse map of billions of galaxies, capturing transient phenomena and revealing subtle patterns in cosmic structure. Its data will enable unprecedented studies of dark energy by tracking how galaxies cluster and how gravitational lensing distorts their light across cosmic time. In parallel, the Euclid Space Telescope, launched by the European Space Agency, is charting the geometry of the dark universe with exquisite precision. By measuring the shapes, distances, and redshifts of galaxies across vast cosmic volumes, Euclid aims to constrain the nature of dark energy and test the laws of gravity on the largest scales. Meanwhile, NASA's Nancy Grace Roman Space Telescope will extend this effort, combining deep imaging with supernova observations to refine our understanding of cosmic acceleration. For dark matter, a different experimental frontier unfolds underground and in shielded environments. Projects such as LUX Zeppelin, LZ, and Xenon-T employ massive tanks of liquid xenon, waiting in silence for the faintest hint of a dark matter particle colliding with an atomic nucleus. These detectors are buried deep within Earth to escape the noise of cosmic radiation, their intricate systems poised to capture an elusive whisper from the dark sector. Other experiments like ADMX and Haystack tune radio frequency cavities in magnetic fields to detect hypothetical axions whose conversion into photons might reveal their presence. These delicate setups push the boundaries of precision, guided by theoretical insights and experimental creativity. In the realm of particle accelerators, the Large Hadron Collider probes energies that might give rise to supersymmetric particles, possible dark matter candidates, exploring the terrain beyond the standard model of physics. Though no such particles have yet appeared, each run refines the limits and suggests new directions for inquiry. The intersection of particle physics and cosmology is fertile ground, where understanding the early universe may illuminate the fundamental constituents of matter. Meanwhile, the synergy between experimental efforts and astronomical observations drives deeper questions. What symmetries govern the dark sector? Are there unknown forces or particles interacting with dark matter or dark energy? Could both phenomena arise from a deeper, unified principle, yet to be discovered? These questions guide the future of physics, shaping the ambitions of the next generation of scientists. As the instruments grow more precise, the data more abundant, and the models more refined, the veil begins to lift, revealing not only the contours of the dark universe but the ingenuity of the human mind, seeking to comprehend it. Dark matter and dark energy not only reshape our understanding of the cosmos, but also challenge the very foundations of physics, pushing scientists to explore radical new ideas and theories. The prevailing cosmological model, known as LCDM, lambda cold dark matter, elegantly combines dark energy, represented by the cosmological constant L, and cold dark matter to explain the large-scale structure and accelerated expansion of the universe. Yet, despite its success in matching observations, LCDM leaves deep questions unanswered, fueling the search for more fundamental frameworks. Alternative theories of gravity, such as modified Newtonian dynamics, MOND, or extensions of general relativity, propose that the effects attributed to dark matter and dark energy might instead reflect changes in the laws of gravity at cosmic scales. These theories attempt to account for galaxy rotation curves and cosmic acceleration without invoking unknown substances. Though intriguing, many of these models struggle to explain all observations simultaneously, especially those from the cosmic, microwave background and large-scale structure, keeping the mystery alive. Other approaches invoke new fields permeating space, dynamic entities that could act as dark energy or interact with dark matter. Quintessence models describe a slowly evolving scalar field driving cosmic acceleration, offering a richer and more flexible alternative to the static cosmological constant. These models imply a universe whose expansion history changes over time, potentially observable through precise cosmological surveys. On the particle physics front, theories such as supersymmetry, extra dimensions, and string theory suggest a hidden realm of particles and forces beyond the standard model. Within this realm might lie the particles comprising dark matter, weakly interacting massive particles, WIMPs, axions, sterile neutrinos, or others yet to be imagined. The interplay between theoretical predictions and experimental constraints narrows the possibilities, guiding the design of detectors and accelerators. Meanwhile, the concept of dark energy intersects with ideas about vacuum energy and quantum fields, raising profound questions about the nature of empty space. The vacuum is not truly empty, but teeming with fluctuations and virtual particles, contributing a baseline energy density. Yet theoretical calculations of vacuum energy exceed observed dark energy by an astonishing factor, the so-called cosmological constant problem, signaling a deep gap in our understanding. Attempts to resolve this puzzle span the domains of quantum, field theory, gravity, and cosmology, often invoking new symmetries or mechanisms to cancel or reduce vacuum energy's impact. These challenges inspire cross-disciplinary research, where cosmologists, particle physicists, and mathematicians collaborate to weave a coherent tapestry of the universe's dark components. The quest to unify dark matter and dark energy with known physics embodies the human drive to comprehend reality's deepest layers. It beckons us toward new horizons of knowledge, where the fabric of space, time, and matter reveals hidden patterns and principles. In this grand exploration, each discovery reshapes our perspective, inviting us to imagine the universe anew. In contemplating the mysteries of dark matter and dark energy, we also encounter profound philosophical reflections about the nature of reality and our place within it. These invisible forces, though unseen and intangible, exert influence on the grandest cosmic scales, reminding us that what we perceive is but a fraction of existence. The vast majority of the universe remains hidden from direct view, accessible only through indirect evidence and scientific inference. This realization challenges anthropocentric perspectives and invites humility, as humanity confronts the limits of perception and knowledge. The dark universe exemplifies the tension between what is observable and what is real, illustrating that our sensory experience provides an incomplete window into the cosmos. It is through the rigorous methods of science, observation, experimentation, and theoretical modeling that we pierce the veil, revealing the unseen scaffolding that shapes all matter and energy. The quest to understand dark matter and dark energy also inspires wonder at the interconnectedness of all things. Though separated by incomprehensible distances and scales, galaxies, stars, planets, and ultimately life are bound within a cosmic web woven by gravity and influenced by dark energies. Expansion. The dance of particles and fields that govern the microcosm connects seamlessly with the evolution of the universe itself, a unity that speaks to the coherence and elegance of natural law. Moreover, the pursuit of these mysteries fuels technological and intellectual progress, driving innovations in detector design, data analysis, and computational modeling. The collaborative spirit of science, spanning continents and disciplines, embodies the collective human aspiration to illuminate the unknown. Each breakthrough deepens our understanding and opens new questions, sustaining an ever-evolving dialogue between humanity and the cosmos. In the end, dark matter and dark energy stand as symbols of the frontier, the edges of human inquiry where certainty fades and imagination takes flight. They remind us that the universe is a vast and dynamic mystery, inviting us to explore with curiosity, rigor, and humility. As we continue to probe these enigmatic forces, we participate in a timeless journey of discovery, one that enriches not only our knowledge, but our sense of wonder and connection to the cosmos. Looking forward, the future of dark matter and dark energy research is poised to transform with the advent of new technologies, collaborative projects, and bold ideas. Next-generation observatories, such as the Square Kilometer Array, SKA, will map hydrogen gas across cosmic epochs, probing the universe's large-scale structure with unparalleled resolution. By tracing the distribution of matter through radio waves, the SKA will shed light on how dark matter shapes galaxy formation and how dark energy influences cosmic expansion. Meanwhile, advancements in quantum technologies promise to enhance detection capabilities. Quantum sensors and entangled systems may increase the sensitivity of dark matter detectors, opening avenues to observe weaker signals and explore new parameter spaces. The integration of artificial intelligence and machine learning into data analysis accelerates discovery, enabling scientists to detect subtle patterns and correlations in vast datasets. International collaborations continue to be essential, pooling resources and expertise to tackle the universe's greatest puzzles. Initiatives such as the Dark Energy Spectroscopic Instrument, DESI, and the Wide Field Infrared Survey Telescope, WFIRST, will complement existing missions, providing deeper insights into cosmic acceleration and structure formation. The theoretical landscape also evolves, with researchers exploring novel frameworks such as emergent gravity, where gravity and space-time arise from microscopic quantum interactions, potentially linking dark matter and dark energy phenomena to underlying quantum information processes. These innovative approaches challenge conventional wisdom and exemplify the dynamic interplay between theory and observation. Ultimately, the pursuit of dark matter and dark energy exemplifies the essence of science, a relentless quest to understand, driven by curiosity, creativity, and the desire to unveil the cosmos' secrets. Each step forward not only enriches our knowledge, but also invites us to reflect on our place within the vast, mysterious universe. The dark universe, once invisible and unknowable, is gradually coming into view, revealing a profound and beautiful complexity that inspires awe and wonder. As humanity continues this journey, the stories we uncover will shape the future of science, philosophy, and our collective imagination, illuminating the path toward deeper understanding and cosmic harmony. As we conclude this expansive journey into the depths of dark matter and dark energy, it becomes clear that their mysteries are not merely scientific puzzles, but profound invitations to rethink our understanding of reality itself. These unseen forces challenge us to expand our conceptual horizons beyond familiar matter and energy, to envision a universe whose fabric is far richer and more complex than previously imagined. Dark matter, silently sculpting galaxies and cosmic webs, reveals the hidden structures that cradle the visible universe, while dark energy, accelerating cosmic expansion, suggests a dynamic, evolving cosmos still full of surprises. Together, they transform the grand narrative of existence, linking the infinitesimal to the infinite, the quantum realm to cosmic scales. The quest to understand these phenomena exemplifies the power of human inquiry, the drive to explore, to question, and to know. It is a testament to the creativity and resilience of scientific endeavor, weaving together observation, theory, technology, and imagination. Each discovery peels back a layer of mystery, yet also opens new horizons, reminding us that the universe is an ever-unfolding story. Beyond the equations and data lie deeper philosophical and existential reflections about the nature of existence, the limits of knowledge, and the interconnectedness of all things. The pursuit of dark matter and dark energy thus resonates beyond science, touching the human spirit and inspiring wonder. As we stand at the threshold of future discoveries, we are reminded that the universe still holds secrets waiting to be unveiled, inviting us to continue this timeless exploration with open minds and curious hearts. In embracing the unknown, we affirm our place in the cosmos, not as passive observers but as active participants in the unfolding drama of existence. The dark universe beckons us onward, its silent depths echoing with the promise of revelation and the enduring quest for understanding.